Hello learners, welcome back to the course on deformation processing of materials. In the previous lecture, we started the high energy rate forming processes, and in that we started with the explosive forming. In that we saw various explosive forming processes like the standoff techniques, contact technique, and the bulkhead forming technique. Also, we saw some of the important explosives which are used in the explosive forming process. And after that, we saw some advantages and the formability of various materials and the limitations, applications, etc. of explosive forming. After that, we saw the electromagnetic forming also. In that, we saw how the setup is made for electromagnetic forming and how the forces are determined. Basically, that is the summation of electric and magnetic forces. So, in that way, total net force is electromagnetic force, and that leads to the deformation. Okay. So today now let us continue our discussion on the electromagnetic forming, and let us see some of the benefits and some characteristics of the electromagnetic forming process. Okay. So let us see some benefits. Benefits of benefits of the electromagnetic forming. So this process requires very low energy, or it has low energy consumption. We have low energy consumption, and the productivity and reproducibility is very high in this case, because we can quickly put the blanks one by one and get them formed. So high reproducibility. Similar kind of shapes can be reproduced frequently here. Okay, and productivity is also higher. So high reproducibility, and productivity. Okay. Also, the tooling and machining costs are reduced. Okay, so only dies, and that too of one-sided type are required here. Okay, so that's why cost is reduced. Low cost due to simple tooling and one-sided dies. Simple tooling and one-sided dies. Okay. And this type of forming process does not require very extreme or high temperatures. It can be conducted at room temperature also. So we have room temperature operation, room temperature operation. Okay, and in this forming process, the risk of wrinkling or shrinking time of defects is very low. Okay, so no wrinkling is there. No wrinkling. Also, the tool and job contact is minimum. So no tool or job contact. No tool, job contact. As this happens in case of other forming processes like forging, etc. forging, rolling, we have the rollers which will be in contact with the workpiece. Here, this is not the case. So no tool job contact. Also, in this forming process, the spring back is very low. Okay, so this happens because the rate of plastic deformation is very high. Okay, so relatively less spring back, relatively less spring back due to very high plastic deformation. Due to very high plastic deformation. Okay. And one more benefit is that the tolerances are narrow, means we do not need very high tolerances. Okay. So we have narrow tolerances. Okay. And in this forming process, the surface finish is very good. Okay. So improved surface finish. Improve surface finish. So these were some benefits of the electromagnetic forming process. Now let us see some of the characteristics of this process. So the characteristics are we are talking about the electromagnetic forming. So electromagnetic forming. Here also we are talking about electromagnetic forming only. Electromagnetic forming. So for this, we need electrically conducting material. That then only the electric and magnetic fields will be induced in it. So the first characteristic is that electrically conducting material should be there. Electrically conductive material. Okay. And the next one is that it is a cold process. Okay. We have seen it earlier also that it can be done at room temperature. Okay, so this is a cold process. And one more thing here is that it is a very high velocity forming. Okay, so this is a process, and this is high velocity forming. Okay, so these are some characteristics and applications we have seen in the previous class, that it can be used for welding dissimilar metals or sheets, and can be used for expansion, compression, or forming of tubular sections. Okay. So before we move to our next forming process under this high energy rate forming, let us see the concept of strain rate. Okay. So basically strain rate is defined as the ratio of crosshead velocity or crosshead speed to the specimen height or sample height. So we'll keep it as a note point that strain rate is given as crosshead speed over the sample height. For example, in case of tensile test, we can take this as the speed of crosshead divided by the gauge length, because there we consider gauge length as the height of sample. So sample height. And units here will be, suppose we are taking the CGS unit, then this will be centimeter per second and this will be in centimeter. So automatically this will come out to be per second. In SI also, this will be per second only. So this was something related to strain rate. Now let us see the next forming process under this category of high energy rate forming processes. Okay. So next one is electro-hydraulic forming. So now let us begin. Electro-hydraulic forming. In this process, the concept of shock wave is utilized to form the sheet metals or materials. So basically, we'll see in the schematic, the blank is kept over the die, and again there is sometimes a medium provided for the transmittance of shock waves, and shock waves are created with the help of electrodes through sparks, and they propagate and reach the blank and deform it severely. Okay, so let us see the schematic that will make it much clear. So let us say we have the dies. So suppose we need to form some shape like this. Say we want to form this shape. So we'll make our die like this only. So say this is our die. And over it, we will place our blank. So this is the die. Here also a single die can be used just to give the shape. And over it, we will place our blank. Blank like this. So this is our blank. And over this, we will create the shock wave. So let us say we have our electrodes like this. So these are the electrodes. Like this. So these are the electrodes. And here a spark will be created. So here we'll create a spark. And this is say contained in a container like this. Okay, and if there is some medium present over here, then it will allow the transmittance or passage of the shock wave, and shock wave will be created and will reach the blank like this. So this shock wave upon reaching here will deform the blank, and the blank will take the shape of die which is placed below it. So these are the electrodes, and this is the shock wave. This is our blank, and here we have cut the die. So how this shock wave appears is uh, basically this is like some loop of waves like this. It is represented like this. These are various wave fronts passing one after the other, and when they reach the blank, they transmit the energy to the blank, which leads to its deformation. Okay. So let us see some more details about the shock wave or concept of shock wave. So we now have the shock wave concept. So in the case of this concept of shock wave, there is something called Mach number. Okay. So we are now seeing the shock wave concept. So before we see various stages and various forms of wave traveling, then before that we will see the Mach number. Okay, so we have Mach number, and it is nothing but the ratio of speed of object to the speed of sound in the given medium. Okay. So this is, and generally we talk about the air medium only. So speed of object divided by the speed of sound. Okay, so this is known as Mach number. We'll see in a while what does this signify. Okay. So this ratio has several values which will uh, define various types of wave fronts form. Okay. So now let us begin or see when suppose both the sound source and the object are stationary. In that case, what will happen or how the wavefront will appear. Okay. So say this is our sound source and it is stationary. Also, the object is stationary. Okay. So again, the wavefront will be simple like this. Okay. Like this. So here both source and object are stationary. Let me use some other color. So both the source and object are stationary. Source and object are stationary. So in this case, the wavefront will appear like this. The next one is subsonic. subsonic wavefront. Okay. So in that case, what happens is the sound source will move at a speed which is lower than the speed of sound. It means the speed at which sound is traveling in the medium is greater than that of the speed of the sound source. And in that case, the wavefront will be something like this. So, see, this is the sound source, and it will be also moving, but the sound will be moving much faster than this. So, let me make it a little clearer. Okay, so this will be something like this, and like this. Okay, so sound will be moving faster than the source. This is the subsonic one. Subsonic. And why we call it as subsonic? Because here the Mach number is less than 1. Mach number less than 1 automatically indicates that the speed of object is less than the speed of sound. Okay, so the sound source is moving at a speed at a speed lower than the speed of sound. Speed lower than the speed of sound. And here the Mach number is less than 1. Mach number less than 1. Okay, so this is the subsonic wavefront. Now, next one is when the speed of the object or speed of sound source is same as that of the speed of sound. In that case, how the wavefront will appear, and that will be known as sonic. Okay, so next one is sonic wavefront. So here what happens is both the source as well as the sound wavefront move with similar speed. So see, this is the source. Okay, so here this will be something like this. Like this. So wavefront will be piled up in front of the source because they both of them are moving with the same speed. So here the wavefront pile up occurs, pile up in front of the source, in front of the source, and the speed of source and object are same. So sound source moves with a speed, is moving with a speed same as that of the sound. Speed same as that of sound. Okay. And here, since both the speeds are same, the Mach number will be 1. So here we have Mach number equal to 1. So this is something about the sonic wavefront. Now, after this, we have the supersonic type of wavefront. Okay, so what happens in that? We have now supersonic. Okay. So here the speed of object or sound source will be much higher than the speed of sound, and it will lead while moving. And due to this, there will be a pileup of these wave fronts along the side of the source. Okay. It will emit the wave front and then move ahead. And in this way, the wave fronts will overlap. Basically, they have trough and crest. So the say crests and troughs overlap with one another. And due to this, a very large amplitude wave is created. And this large amplitude wave is known as shock wave. Okay, so it has very high amplitude, and due to this, it may lead to deformation here if it reaches the blank. Okay. So how will it appear? Say this is the source which is moving, and it is creating the wave fronts, and these are now, they will get amplified also over the time. They will say this is emitting and moving. So this will be something like this. Okay, and here the wave fronts will start piling up like this. Like this. So they are now overlapping. So say this is like this for one wave, another is we have like this, so like this. So they will ultimately pile up and will give large amplitudes like this. Okay. So here the wavefront pile up along the side. Wavefront pile up is there along pile up along the side. Okay. And also, as I have mentioned, that the wave crest overlap one another. The wave crests overlap one another and form a large amplitude wave, and form a large amplitude wave, which is known as shock wave, which is known as shock wave. So this is how shock wave is created. Let me highlight this also. So this is the creation of shock wave. Okay. And here the Mach number will be obviously greater than 1, because speed of the object is much higher than that of the sound. So Mach number is greater than 1. Okay. So this falls in the supersonic range. Okay. Now, based on this concept, let us see an interesting fact that when the space shuttle re-enters the atmosphere from the space, it has a Mach number of 25. So that is extremely high. Okay. So that's why when the speed is that much higher, the materials out of which the space shuttle is made should have very high thermal stability. Okay. So let us put this as a note here. So this is a fact or note that when space shuttle re-enters, when space shuttle re-enters the atmosphere, re-enters the atmosphere. This will be re-enters atmosphere. it has a Mach number of 25. Okay. And while moving with this much high speed, so while moving with this much high speed, it should have materials. It should have materials with very high thermal stability. Materials with very high thermal stability. Okay. So this is a fact very well known related to the re-entry of space shuttle. Now let us see or form a table of various Mach numbers and speeds, and what are the categories called when the speed of object reaches that much value. Okay, so let us see that when the Mach number, here is Mach number, here we have speed, and now let us see what are the values for, say we have firstly subsonic range, so subsonic, then we have next one is transonic, so we have transonic. After that we have supersonic. Okay, so we have now supersonic. Above this we will have the hypersonic range, hypersonic, and after this we have seen highest is the re-entry, okay, re-entry of space shuttle. So re-entry is here. So Mach number here is generally 0.8, and the velocity range is, so this is 0.8 or less than 1, and here the speed will be say lower than 273 meters per second. For the transonic, it will be nearly 1, so this will vary from say 0.8 to 1.3, and the speed will be around 273 to 409 meters per second. Okay. And after this, in the supersonic range, we will have this Mach number ranging from 1.3 to say 5, and the speed will be above this say 410 to around 1700 or 1800. So 1700, 2 is the number, yes, 1702 meters per second. And in the hypersonic, we have this Mach number in the range of 5 to 10. Okay, so this will be 5 to 10, and the speed will be 1702 to say 3403 meters per second. Meters per second. And here the Mach number will be, in case of re-entry, it will be say equal to or higher than 25. Okay. And here speed will be also very higher, say it will be more than 8500 meters per second. This is a very high speed. So these are some values for various ranges like subsonic, transonic, super, hyper, and re-entry. Okay. So also we have seen that the deformation rate is very high. Okay. So uh, in this process, in this deformation process, the rate of deformation is say not less than 1200 or 1500. Okay. So the rate of deformation is not less than 12 to 1500. 12 to 1500. And again, the as we have seen frequently shock waves, so the velocity of shock wave has a relation which is given by shock wave velocity is given as say u will be nothing but a plus b times u2. Okay, so here u is the shock wave velocity itself, u2 will be the velocity of object or particle, and a and b are material constants. Okay, so here u is shock wave velocity, u2 is particle velocity, and a and b are material constants. Okay. Material constants. Material means the medium which is transmitting the shock wave or through which the shock wave is passing. Okay. So uh, this particle velocity is very low or less than the shock wave velocity. Okay. So if we see the spectrum distribution, so shock wave velocity will be something like this or this very high values, and this particle velocity will be something like this much lower. Okay. So this is the shock wave velocity, and this will be our particle velocity, which is very low as compared to the shock wave particle velocity. Now, this technique we have seen is used for deformation processing. Okay. One more interesting application of this technique is to rejuvenate the clogged bore wells. When bore wells to take out generally to take out petroleum, this is adopted. Okay. So when there is a cloggage in the bore wells which are drilled for petroleum extraction, so in that case a shock wave is sent there and it cleans or clears the clogging, and petroleum then comes out. Okay. So let us put this also as a note that this technique of shock wave, this technique is utilized, this technique of shock wave is utilized in the rejuvenation of clogged bore wells, clogged bore wells to take out petroleum, to take out petroleum. So if we draw or represent it schematically, then how it happens is, say this is the drill bore way, okay, like this, and suppose here what happened? Suppose here there is a clogging like this. Clogging like this. Let us draw it a little lower. In the bore there is some clogging, and below this lies the petroleum. See, this is petroleum. And above the clogging there will be water, because water is generally present at higher levels than petroleum bed. So here we have water, and if not, then we will put some water to transmit the shock wave. So this is like this, and in order to create the shock wave, we know that we need electrodes there, okay, to create the spark and then shock wave. So say we put the electrodes here like this. So these electrodes now emit the shock wave, and this shock wave will now clear the clogging. Okay. So this is the electrode, and this is the water medium. This is the shock wave created. Shock wave, and say this was the clogging, and this is petroleum. So this is one more application of this shock wave technique, and we have seen how it is used to shape or deform the materials in metal forming operations. So with this, we can now conclude the high energy rate forming processes. Okay, so now let us quickly see some briefing about the latest techniques used for deformation, which is also known as severe plastic deformation. Okay, so in that there are several techniques, but we will focus on the ECAP process. Okay. So now let us see severe plastic deformation. So we have severe plastic deformation, and this is abbreviated simply as SPD. SP. So in this we will see the ECAP process, which is also known as equi-channel angular pressing. So ECAP or equi-channel angular pressing. So this is a technique in which very high or severe deformation is given to the material so as to refine the grain size, and which ultimately increases its strength. Okay. So in this, the metal is subjected to intense plastic straining. So let me write it here, that metal is subjected to and intense plastic straining, and that too through simple shear without any change in cross-sectional area or dimensions. Okay, here, the target is not to change the cross-sectional area or dimensions of the sample. Plastic straining through simple shear without any without any change in the cross-sectional area or dimensions in the cross-sectional area or dimensions of the sample. Okay. And due to this forming process, the grain size reaches below some nanometers. Okay, so it reaches to say nano size. Okay. So the grain size reaches to the nanometer range. To the nanometer range. Generally, this is less than 500 nanometers. So you can see how much refinement is possible through this. Okay. So now let us see through a schematic how this is carried out or how this is done. Okay. So say we make channels. Okay. So say this is a channel, and this will have a bend that will cause the deformation or lead to the deformation. Okay, so this will be something like this. This is the channel through which the sample will be passed. Say this is our sample. Like this. And it is pressed through a plunger which will press it down and will cause it to pass through this bent channel. So say we have a plunger like this. Let me use some other color. So we have a plunger like this. So this will be pressing the specimen down through the channel. This is like this. And after passing through this channel, the sample will get refined. So say this is the deformed specimen. So it will get refined. So this is our specimen. Again, this was our sample or specimen. Yes, so there are some terminologies related to this. So let me label the diagram. This is the plunger, and this is our sample. And there, this channel is say kept in a setup or system where entire thing is done. Okay, so this is usually separated or packed type of thing. And this angle here, this bend is known as the channel angle. Okay. So this is the phi, which is nothing but channel angle. Channel angle. And this is usually this takes the values like 120 degree or 90 degree or 60 degree. Okay. And here this angle has also its own significance. Okay. So say from here we can measure, or from that side also we can measure from here. Okay, so this is the angle of curvature. Okay. So this is represented by psi. Okay. So this angle is psi. Let me write it like this, psi, and this is the angle of curvature. Angle of curvature. And this will be our sample after. Here also several passes can be done. Okay, so this is say after single pass we are seeing. So this is sample after first pass. So sample after first pass. Okay. So this is the schematic arrangement for this ECAP process. And here what happens is that the grain size gets refined. Okay, so as I mentioned, how this happens, let us draw that also schematically. So let me use this area. So here what happens is, suppose initially my grain size was like this. So these are the grains. These are the grains initially. Like this. So after this ECAP process, these get refined. So like this, fine grains are formed. So they get refined. Like this. Size means the dimensions and cross section will not change. Grain refinement will be there. Okay. And uh, this this cannot be repeated frequently. Means after a certain number of passes, the strain becomes constant and there is no more straining. Okay. So after a specific number of passes, specific number of passes, the strain becomes constant. So the strain becomes constant. Okay. And the value of strain after say n passes is given as, though this is a relation which is means the derivation of this relation is out of scope of this course, so we'll see the relation only. So the strain after n number of passes, after n passes is given as, say this is En, and this is nothing but n over root 3, okay, into 2 times cot of this phi by 2 plus psi by 2, phi by 2 plus psi by 2, okay, plus psi times cosec of pi by 2 plus psi by 2. So here all the number of passes and the uh, channel angle and angle of curvature are all important. So this gives us the strain after n passes. And as I mentioned, this angle of channel or channel angle can take values like 120 degree, 60 degree, 90 degree, etc. Okay. And basically the strain accumulation process occurs only in the bend region. And in the other sections of channel, no straining occurs, means the material simply passes. But when it passes through the bend, at that stage only the straining occurs. Okay, so the strain accumulation occurs only in the bend region. Occurs only in the bend region. And again, in this process also, after the deformation, the end of the material are not deformed completely, means there the desired deformation is not achieved and they need to be cut off and thrown. So like suppose we have a cylindrical sample like this. Okay, so this portion, say this much portion at the end is not deformed, okay, and this need to be cut. Okay, so this portion of the sample is not deformed. This portion, or this is the end portion, okay, is not deformed and is cut. Okay. So this is how the ECAP process is carried out. So now let us see some of the characteristics of this ECAP process. Okay. So we'll now see the characteristics of ECAP. So here we have seen that a very significant amount of strain is imposed on the sample. Okay. So significant amount of strain is imposed on the sample. Okay. And also we have seen that there is no change in the cross-sectional area or dimensions. Okay, so the cross-sectional area remains unchanged. Okay. Remains same. Okay. And the stress is accumulated in a small region. Okay. So stress accumulation in small region. Small regions. Okay. And let us also see how the behavior changes after ECAP means through the stress strain diagram, which is a classical way to see the change in strength, etc. Okay. So we have stress strain after ECAP. Okay, so here we can observe that the strength of the material increases, whereas the percentage of elongation or ductility decreases. So say we have the annealed specimen. So for that we will have the stress strain graph like this. Okay. So this is the typical stress strain behavior for an annealed specimen. But after ECAP, say let us see after some 3 or 5 passes. Okay, so after 3 passes, okay, let us say, so after 3 passes, this is yes. So after 3 passes, this becomes something like this. Okay. So the strength increases, but at the same time, the ductility decreases or elongation decreases. Okay. Like this. And similarly, if we keep on increasing the number of passes, then what happens is it will further be like this. So, say here we have increased the number of passes, ECAP process. Okay, so this is our stress, and here we have the percentage strain. Strain. So here we have the strain. Okay, and say this is 7%, this is 10%, this is 35%, etc. Okay. So this we had for annealed one, and this was for 3 passes. Okay. ECAP, and this is for say 5 passes. Okay. So 5 pass. ECAP. So this is how the stress strain behavior is observed. So this is some of the characteristics of this ECAP process. Okay. So with this, we now come to the end of this ECAP process and also to the end of this course. So I hope you would have learned a lot of things about these deformation processes and deformation behavior. And thank you for learning from this course. Okay. Thank you so much. Now we conclude the course here.